Hello and welcome back to this third video. In this video, we continue with chapter 0 and we move to section 0.2 about general topology. Now, for the most part, this section will be a review, but it's very important to understand the basics of a general topology if you want to understand functional analysis. Okay, so this material is very important, but I will start from scratch. So this section is divided into 3 subsections. The first one is a little bit lengthy, so I will divide the video maybe into 2 or 3 parts. From metric spaces to topological spaces. So I will assume that you know something about metric spaces. And because the course on general topology is optional here, so maybe not all of you have taken this a course on general topology. Okay, so we know that metric spaces are very important in analysis. However, they are not enough. Sometimes one needs to consider spaces where a topology is not given by a distance, and this we shall see this especially in chapter 4. In a metric space, we have the notion of convergence, continuity, compactness, and so on. If you look carefully at these notions, you will see that they don't depend directly on the notion of distance. Rather, they depend on the notion of an open set. Okay, so this will be our starting point from metric space to topological space. So, but what is an open set in a metric space? If you have a metric space X, D, let us say, what does it mean that a subset of X, O, is open? It's open if whenever we have a point in O, there is a whole ball of center X contained in O. Okay? So this is the definition. Of course, not all sets are open usually. Now, a remark, we know that the open ball of center X and radius R is contained in the closed ball of center X and radius. So this is the notation for closed ball. Okay, so BXR is the open ball of center X, radius R. B prime is the closed ball. And so an open ball is contained in a closed ball, and the closed ball of center X and radius R over 2 is of course contained in the open ball of center X and radius R. So the condition of openness is equivalent to saying that for every X in O, there exists a closed ball of center X contained in O. So the two conditions are equivalent. So we can put open ball or closed ball, doesn't matter actually. So just a ball. Okay. Now, of course, an open ball is an open set. We know that. And in the second year, we proved that according to this definition, the empty set and the whole space are open sets. An arbitrary union of open sets is an open set as well. So satisfies this condition that I wrote here. And a finite intersection of open sets is also an open set. So note the difference between condition 2 and 3, properties 2 and 3. The union is arbitrary, so any collection. However, in the intersection, we have to take a finite intersection. And this is equivalent to just requiring that the intersection of 2 open sets is an open set, because then you just use induction actually. Okay, so we know that from second year. And now this was a theorem actually, or a proposition in metric topology. And to move to more general spaces, we take this proposition as a definition or an axiomatic definition of a topology. So if we denote by calligraphic T the union of open sets in a metric space, we can restate this proposition, what we said before, in the following way. So if T denotes the collection of open subsets of a metric space X, then the empty set and the whole space belong to this collection, this special collection, and T is stable under arbitrary union. So if we have a collection of sets of elements in T, then their union is also in T. And third condition, the intersection of two elements of T is in T. Okay, so we say that T is stable under finite intersections. Okay, and now we take this as a definition. So a topology on a set X is a collection satisfying these three properties. Okay, so, and in this case, the elements of T are called the open sets of X, well, open relative to the topology. Of course, we can put several topologies on the same set. So, as usual, let us give examples. So, a topological space is a couple, is a set equipped with a topology. The topology is therefore a special collection of distinguished subsets that are called open. So a metric space is a topological space according to what we said in the beginning. The converse is not true, and I will tell you why in a moment. Now, the topology defined by a distance is called the topology generated or induced by the distance. Okay? Now, if we have a topological space, xt, we say that T is metrizable or X is metrizable if T is generated by a distance. Okay, this is an important concept because here we have to distinguish between topological space and metrics. So topological space are, of course, topological spaces are generalizations of metric spaces. So we say that the space is metrizable if this topology, which is given, is generated by some distance. And of course, the distance need not be unique. Okay? And we'll see that not all spaces are metrizable. Not all topological spaces are metrizable. So this is why topological spaces are really in a bigger space, a bigger class of sets. Okay. Another example, trivial. If you have a set X and you consider the collection consisting of just two elements, so a finite collection, just two elements, the empty set and the whole space. According to our definition, this is a topology because it contains the two extremes. Any union of these two elements, a union of the empty set and X is X, of course. If all the elements are empty, the union is empty. If one of them is X, then the union is X. The intersection, if one of them is empty, it's empty. If all of them are X, then it's X. So this is really a trivial case. This topology is called the indiscrete topology. This is actually the smallest topology that one can put on a set. Okay? And this topology is not metrizable. It doesn't come from a distance. Okay? And I will tell you why in a moment. Another example, another extreme case, is the collection of all subsets of X. It's called the discrete topology. So a topology is always included between these two extremes, between the indiscrete and the discrete. Now, of course, P of X is a topology because as it contains everything. So this is also a trivial example. And it happens that this topology is metrizable because recall that we defined the discrete distance, which is 1 if the 2 points are distinct and 0 otherwise. It's very easy to check that this is a distance. We did that in second year. And now if you consider the topology generated by this distance, it is exactly P of X. Okay? If you forgot the proof, just pause the video and check that. It's a good exercise. but I will give you the idea. I will help you a little bit. Okay, if you consider this distance, what is the ball of center x and radius 1? If you write the definition, you will see that the ball of center x, the open ball of center x and radius 1 is precisely the singleton x, so it's just the center. But since open balls are open sets, then we have that singletons are open. If singletons are open, then all subsets are open because a set is the union of its singletons. So this means that the topology generates, so if every set is open, then the topology just P of x. Okay? You can take another distance, for example. You can take the distance 2, 0 if you like. This is also another distance that generates the same topology. Okay? So, as you said, any topology on a set is between these two extreme and trivial cases, the indiscrete and the discrete. Okay? We say that the indiscrete topology is the smallest or coarsest topology on the set, and the discrete is the biggest or finest topology on a set, and we will come back to this notion of comparison of topologies later. Another example, if you consider an arbitrary set X and the subset A of X, and we consider the collection consisting of just 3 elements, so it's a finite topology, just the empty set A and X. Now, that is also trivial that it's a topology because it contains the two extremes, empty set and X. If we take an intersection or union, let us say, if one of them is X, then the union is X, of course. If none of them is X, then, and of course, if all of them are empty, then the union is empty. If one of them is A, and none of them is X, then the union is A. So this collection is stable under unions. Okay, so no matter how you take unions of elements between these 3, their union will be one of these 3. And for the intersection, it's the same thing. Okay, so it's a topology, trivially. And this topology, again, is not metrizable. Okay, it doesn't come from a distance. Another example, the 3-point set ABC. So we assume that they are different, distinct elements, ABC. And now we consider also a finite topology consisting of 4 elements: the empty set, the singleton A, the set AB, and the whole space ABC. Then, as you may check mentally, this is also a topology because first condition is trivial. Union, if you take any union of these 4 elements, the union will be one of these 4. Okay? And the intersection will be also as well one of these 4. Okay? So this is a topology and this is not metrizable as well. I will tell you why. 6th example, the finite complement topology. So here a set is said to be open if either it's the whole space or its complement is finite. So an element belongs to T, a subset of X belongs to T, U, let us say, if either it's equal to X, if either it's empty or its complement is finite, so same thing. So here I'm saying that the complement is finite or the complement is equal to X, which is equivalent to saying that U is empty. So we must include the empty set, otherwise it's not a topology. So what are the open sets of this topology? They are the empty set, of course, and sets whose complement is just a finite set. Okay? This topology is called the finite complement topology. Okay, let us prove this quickly. So as we said, the empty set belongs to T by definition, right? The whole space belongs to T because the complement of the whole space is empty, and the empty set is considered to be finite, contains the 0 elements. Okay, now suppose that we have an arbitrary collection O alpha of elements of T, and let us prove that the union is an element of T. So we look, of course, if all of them are empty, there's nothing to prove actually, because if all of them are empty, then the union is empty. Okay, so we look at the complement. The complement of the union by De Morgan's law is the intersection of the complements. Okay, so of course here we can assume that none of them is empty, because if one of them is empty, we can remove it from the collection. It doesn't change the union, right? So we can consider a smaller collection. We remove the empty sets. So we can assume that actually none of these elements is empty. So O alpha is not empty. So since it's open, then its complement is finite. So the complement of the union is the intersection of the complements, and then this is an arbitrary intersection of finite sets. So it's of course a finite set as well, because it's contained in a finite set. Okay. And for the intersection, same idea. If one of them is empty, the intersection is empty, and therefore it's open. So we assume that none of them is empty, and therefore the complement of O1 is finite, the complement of O2 is finite, therefore the union is finite, but the union is the complement, so De Morgan's law again. So we have to rule out the trivial case, okay? So according to our definition of a topology, this is a topology as well, okay? Seventh example, the countable complement topology. Same thing, just replace finite by countable, which is more general. So once again, you can prove according to these lines. Of course, as you said, you have to rule out the extreme cases where one of them is empty, so you remove the empty sets. Okay, so you can always assume that the elements are not empty. And if you want to prove that a collection is a topology, you take an arbitrary collection of elements of this collection, and you may assume that none of them is empty after removing the empty elements. So we have also the countable complement. These topologies are basically used for counterexamples. They are not very interesting. Okay. The discrete topology is more interesting actually, although it's an extreme case. Okay. So we have now the finite complement topology and the countable complement topology. Of course, which one is bigger? The countable complement topology is bigger, right? Because if you take an open set in the finite complement topology, its complement is finite and therefore countable. So a set in this topology is an element of this topology is an element of this topology. So this is bigger. Eighth example, the particular point topology. This is also a topology used for constructing counterexamples. So it's not interesting. We fix a particular point A in a set X, and we consider the collection of all subsets U of X that either are empty or contain the set A. So a set is open if either it's empty or contains A. Okay, so all non-empty open sets have a common point, which is A. And once again, it's trivial to check the three conditions. Okay? It's straightforward, actually. And this is called the particular point topology. It's also used for counterexamples. Now, the subspace topology, if we have a topological space Xt and a subset Y of X, then Y inherits, so to speak, the topology of X. What is this topology? It's called the subspace topology. If you consider the collection of sets of the form Y intersected with O, where O is open in X, okay, then this collection, as you may check, this is a topology on Y. Just pause the video and check that if you don't believe me. So this is a topology on Y, and this topology is called the subspace topology of Y, sometimes the topology inherited from X. Now, of course, on Y we can put another topology, but the one that we call the subspace topology is this one. Okay? So what are the open sets of Y in this topology? The open sets of Y are the intersections of Y and the open subsets of the bigger space X. And this may be confusing. For example, if you consider 0, 1 as a subspace of R, when we say nothing, it means that R is equipped with the usual topology, which is generated by the usual distance, x minus y, an absolute value. Okay? So if we take here x equal R and y equals 0, 1, and now we consider, call it A, the semi-open interval 0, 1 half. Then 0, 1 half, closed in 0 and open in 1 half, is not open in R, but it's open in the space 0, 1 in Y. Why? Because you can write, for example, 0, 1 half as the intersection of 0, 1 with the open interval minus half, half. Of course, it's not unique because we can write this as 0, 1 intersected with minus 1/3, 1 half, if you like. Okay, so we say here that this set 0, 1 half the semi-open interval is open in the closed interval 0, 1, but not open in R. Okay, so we have to be careful when we say open. So we say that 0, 1 half is relatively open. Okay. It's very important, this notion of subspace topology. Now, comparison of topologies. If we have two topologies on the same set X, T and T prime, calligraphic T and calligraphic T prime, if T prime contains T, we say that T prime is finer or stronger sometimes, or just bigger. So bigger, finer, stronger, same thing. Okay? And in this case, we say that T is coarser or weaker or smaller, same thing. Now, of course, not any two topologies are comparable. Comparable means one contains the other. Okay? So let us give some quick examples. If we consider the 3-point set ABC and we consider 3 collections, the first one contains 4 elements, empty set A, ABX, we know that this is topology. A second collection, empty set A, B, AB contains 5 elements, and the last one contains also 5 elements. Okay, which one of these are comparable? Okay, T2 is finer than T1 because it contains one more element. Okay, so T2 is finer or bigger. However, T1 and T3 are not comparable. Okay, we cannot, so T3 doesn't contain T1 and T1 doesn't contain T3, so they are not comparable. And T2 and T3 are not comparable as well. Okay. The finite complement topology on R is weaker or smaller than the usual topology. Why? You tell me why. Try to guess. How do you prove that the finite complement topology is contained in the usual topology? Okay, how do you prove that a collection is contained in another one? We take an element of the collection. So take a set in the finite, an open set in the finite complement topology. If it's empty, then of course it belongs to the usual topology. So if it's not empty, then the complement is finite. But we know that finite sets in R in the usual topology are closed in the usual. Yeah, I didn't explain the notion of closed, but you guess. A closed set actually is a set whose complement is open. Okay, so if you like, it's easy to prove that if we just take singletons, if you like. Okay, if you take a singleton, the complement of the singleton is an open set for the usual topology, right? So therefore, Yeah, so the intersection, okay. We need it's better to use the notion of closed sets here, because finite sets are closed in the usual topology of R. Therefore, the complements is also open, right? And you already observed that the complement topology is contained in the countable complement topology. However, the countable complement, the usual topology and the countable complement topology are not comparable. Okay? So you can give an example of a set open for the countable complement topology, but not open in the usual topology, and vice versa. Okay? Try to think of something like that. Okay, now we come to the next topic, which is the basis for a topology. A basis for a topology plays the same role as the notion of collection of balls in a metric space. But as you said, in a topological space, we don't necessarily have the notion of distance, and therefore we don't have the notion of a ball. Okay, so we want to extend this notion to this more general context. Okay, so let us analyze the properties that the collection of balls possess. So first of all, every point belongs to the ball of center this point. Okay, so this is trivial. And the intersection of two balls, while not necessarily a ball, certainly contains a third ball. We saw this. You can draw a picture, of course. So you just take one ball intersected with another ball. The intersection of these two balls is not a ball, but if you take a point in the intersection, you can find a smaller third ball contained in the intersection. We did that in second year. Not terribly difficult. And I take these two properties now as a definition of a basis. Yeah, actually, I wrote the proof here. Yeah. So if we consider the intersection of two balls, okay, BAR and BBS, right? So we can find a third ball of center X and radius delta contained in the intersection, as you can see on the figure. And how to choose delta, it's not difficult. Just take the minimum between R minus the distance between X and A, and S minus distance between X. But it's better to see it on the figure, of course. And we did a lot of such things in second year. Okay, and now we take these two properties as a definition. So if you have a set X, a subset of P of X, or a collection of subsets of X, is called a basis for a topology if every element of X is contained in some basis element, and the intersection, if you have a point in the intersection of two basis elements, then there is a third basis element containing X and contained in the intersection. So like the same thing, okay? Okay. So the elements of the basis are called the basis elements. So you can always think that basis elements are just substitute of balls. Okay, and now what is the topology generated by this basis? If we have a basis, then we can define a collection calligraphic T as follows. A set O belongs to T, to calligraphic T, if whenever X is in O, then there exists a basis element containing X and contained in O. So exactly like the definition of an open set in a metric space. So it's a generalization. But now we just have to check that this is indeed a topology, okay? And it's here where we use the condition 1 and 2. So please do it. It's just a copy-paste of the proposition that we started with in the beginning of this video. So you do it. So it's indeed a topology, and it's called the topology generated by B, calligraphic B. So let us just give a few examples. So of course, as we said, in a metric space, the collection of balls is the basis for the metric topology. We know that. And therefore, the collection of open disks and the collection of open squares are basis for the usual topology of R2. Why? Because open squares are actually open balls with respect to, now, open disks are open balls for the Euclidean norm. But as you know, we have other norms or other distances on R2. We have the one norm and the infinity norm. So, and we know that the balls for the infinity norm and open and the one norm are actually open squares, as you know from first year and second year as well. Okay. Another example, if you consider the collection of singletons of X, then as you may check, this is a basis, and it generates the discrete topology on X. Okay, so write the details if you like. Third example, the collection of all open intervals AB of R is a basis for the usual topology. Why? Because in an open interval, AB is just actually a ball of the center of the midpoint of AB. So if X is AB plus A plus B over 2, and R is B minus A over 2, then AB is just X minus R, X plus R. So the collection of intervals is actually coincides with the collection of balls of center X and radius R. So this is another way to see the usual topology of R. And more interesting examples will be seen later when we deal with the product topology. Okay, and now a result about bases. If calligraphic beta is a basis for a topology T, then every element of T is the union of elements of B. And so this is why we call it a basis, actually, because so a basis, if you like, is the building block for a topology. So, okay, so the open sets are actually unions of these bricks, if you like. And second thing is that T is the smallest or coarses topology that contains B. And if we want to prove if T prime is another topology, this is a methodology actually, if T prime is another topology on X, then, and you want to prove that T prime is finer than T, then it's enough to prove that T prime contains B. This is also trivial. Okay, so I suggest that you pause the video and try to prove this on your own. So it's just an exercise in set theory and logic. Okay, so not terribly difficult. Just try it. And if you already took this in the course on general topology, then you just can disregard this. Okay? Yeah. Now, I think I can stop for this video now because I don't want to make lengthy videos. So I will stop here and continue with the same section in the next video. So thank you for your attention.